try, but I don't think you can do that.
And it's in progress now.
Okay, so it's in progress. Now it works.
The power.
Yes.
Okay.
So
So
now,
once-
Luca, you are the host. So now you have the thing. Okay, fine. You can
So
go
once
on.
again, we can define the matrix S11 is defined exactly in the same way as before. I appreciate that n is big, but the matrix S11 is defined in the same way. We can study the eigenstructure of this matrix. The largest eigenvalues will diverge as before, like T1 plus 2 over eta, same as before. But now n kicks in, and so we have this almost sure lower bound that you see here, where n plays a role linearly. The increase is with n to the power of 1. On the other hand, the other eigenvalues, the smaller ones, are bounded by nt to the power of 2 over eta. The role of t is the same as before. Whether n is finite or infinite, t doesn't care. N enters equations 22 and 23 with very different disguise. In the former case, it's n to the power of 1. In the latter case, it's n to the power of 2 over eta. My main concern here is this an eigengap? Is it really true that the guys in 22 are bigger than the guys in 23? Or better, when are the guys in 22 bigger than the guys in 23? If you just look at the rates that you see here, it is possible to show that we have an eigengap under equation 24. Equation 24 tells me that n and t cannot go to infinity arbitrarily, but there must be a restriction on the relative rate of divergence in particular. If eta were equal to 2, so we are in the domain of attraction of the Gaussian law, so we are in the by and Eng case. If eta is equal to 2, essentially this is n to the power of 0, so essentially all I need is t to go to infinity. But when eta is smaller than 2, I am in the domain of attraction of a non-Gaussian law, and then I do need a restriction between n and t, and the smaller eta becomes, the heavier the tails, the less I am able to detect the presence of common stochastic trends when n is big. N is to be smaller and smaller and smaller. Otherwise, these small eigenvalues will act as a confounder for the big eigenvalues. If you accept this restriction, could be interesting because, like I said, in the case of finite variance, we didn't need it. Then it is perfectly possible to replicate exactly what we did in the previous paper. We consider a slightly different test statistic, which is one that Matteo and I studied in a paper in the case of finite variance. And it is given essentially by the eigenvalues of Sjj, suitably normalized to make them scale-free by the eigenvalues of S00. You have my promise that this guy goes to infinity when this eigenvalue is big, so under the null that this guy goes to infinity. You have my promise that this guy goes to 0 when this guy is not so big, and so it gets drowned out by the denominator. And then we can take this guy, which is big under the null, small under the alternative, and make it super big under the null, and still small under the alternative. We can randomize this object, as we did earlier on. We can cast these objects, the randomized tests based on them, in a sequential procedure, and develop an estimator for m, which we call m something. And we have this consistency result for m something, which is very, very similar. The similarities with the small n case are striking. The only difference is in this relative rate of divergence, I think. So yes, it is possible to study the large n case thoroughly for the case of a large factor models, and it is still possible to say something in the context of a genuine large dimensional vector error correction model. Now I have 5 minutes, so I mean I've wasted time being waffly, so it's my silly fault. But if I
say
could
a little bit more than 5, since there was that interruption, so
5.5.
okay.
Okay, so I would like to say something brief about the Monte Carlo, just to tell you that it works well. In fact, you know what? I'll show you some numbers from the paper briefly, quickly. I apologize in advance, but then I would also like to show you something coming from the empirics, which is not my forte. I think you can see a table, can't you? Can you see a table? Can you see a
Yes, I
table?
can
You
see.
see a
Yes,
table.
yes. We see
Now
it,
look at
we
the
see it.
table, because this is the true m, and this is the estimated m. N is equal to 3, so we are in the small m case. And the estimator doesn't do that badly. This is the percentage of times that the estimator is equal to 3 when the true m is equal to 3. And if you look across the board, it could be worse. And then when n is equal to 4, look at this number for a second. Second is gone. When n is equal to 4, look at this number. When t increases, things improve. But look at this number, not at this number. And when n is equal 5, keep looking at this number. When n is equal 5, look at this number. And then look at this one. When t increases, things go well. Thank goodness for that. Agreeing with our theory. When n increases, the performance of our small n estimator of m deteriorates, and we need a bigger t. And this is especially true when the tail index is very, very small, which is in agreement with the theory. The theory was stipulating that when eta is very small, n has also to be very small. We considered an estimator which was tailored to the large n case, also to improve this, and therefore, I'll just show you some numbers. I'm sorry, this is not exactly what you would call a professional presentation, but you can consider here what happens when t increases and when n is equal to 20 or 50 in the context of the estimation of the number of common stochastic trends. This has to be finite, typical of factor models. This is the estimated value. And these are our results. As you can see, results deteriorate as eta decreases, they improve as t increases, and they tend to be worse a little bit as n increases. Everything seems to be in agreement with the theory. In the paper, in the main version of the paper, we also consider two applications. I don't know if it is a good idea to show them or not. I hate presenting tables, by the way. I think that it is acutely apparent that I hate doing it because I'm not very clever at doing it. This is an exercise that we did where we tried to, let me talk for 2 minutes, where we tried to determine the number of common stochastic trends in the presence of 7 commodity prices. You can see the commodity indices here. You can see that if you do a test for the null hypothesis that the variance is infinity, you always accept the null. So I'm sorry, but the variance is infinity here. You don't have the variance, so to speak. And so in this case, when you use your Hansen's methods, you will get a wrong estimator. In particular, here you will see this is the rank of cointegration. N is equal to 7. So here you see 5, 6, 7 common stochastic trends. Here you see the absence of cointegration. When you use our procedure, the number of common stochastic trends is not equal to 7, so there is cointegration. Overwhelming evidence that there are 3 cointegration relationships, 7 minus 4, because there is overwhelming evidence that there are 4 common stochastic trends. And then we also do a more nitpicking estimation of the cointegration relationships in the, where are they, 1, 2, 3 oil prices separately, 3-dimensional system, and in the metals, copper, gold, and the other 2, 4-dimensional system. And this disaggregated analysis seems to confirm that in the case of oil prices, there is There is one common stochastic trend, possibly two. Well, there is one co-integration relationship, maybe two. Whereas in the case of the metal prices, it's 4 of them, and there seem to be 3 common stochastic trends, so one co-integration relationship. This is just to say that the results coming from our theory are not 100% in agreement with the results coming from a Johansen test, which is employed under the incorrect assumption that data have a finite variance, which is anyway not supported by the data themselves. I would like to now go to the last slide just to say, well, thank you very much for your attention, and I think that I have taken 1 minute longer than I wanted, so my apologies for that. I hope you had fun, and any questions, I'm here in front of the screen, as you will have deduced. Thank you.
Thank you, Lorenzo. So we still have time for questions, of course. I think we can do the following. Luca, if you make me host and not co-host, then the recording will be stopped automatically. So then we can have questions with video on and everything. I think that would be the easiest thing, so that you don't need to type questions on the chat, but we can have an open discussion. I don't know if you managed to do that.
Okay, so
Make
can I
host. Make me
host?
Host. Yes, if you click on my name,
Yeah, okay.
and there is
okay.
more. I can get it by myself. Okay, got it. No problem. Okay, now I should be able to stop everything. All the recording. Hopefully, it doesn't. I don't know how to stop the recording. Well, so let's keep the mic, the cameras off, and you can ask questions with the cameras off. I think that's the only option.
But I will be able to cut, I hope, the video later
yes,
on.
okay, Francesco, thank you. You are here. I haven't seen you. Okay.
Because I was a camera off, exactly.
Yeah, no, because I see Francesco, but I don't see only Francesco. Okay. Okay, so go ahead if you have questions, if anyone has questions. I cannot ask them,
No, you can, come on.
It doesn't make much sense.
Can I raise my hand?
Yes, of course, Paolo.
Ciao.
Ciao.
So this is a silly question, not because the paper is silly, to the contrary, no? So is there any optimality theory? I mean, what you seem to be engaging with is trying to get something in the face of difficulties with, you know, thick tails. But, and I understand that you don't want to do the nitty-gritty of estimating this tail index and all this. But in a sense, how do you choose what to do, in a sense? I understand somehow the motivation that you give in the presentation is more like convenience, because conveniently we can sort of get rid of, we scale, we do this and that. But is there any theory that you can sort of revert to say, this is what we should do optimally? Or, I don't know, this is like an oracle property or something like that. Stupid question, but hopefully you have understood what I meant.
Yes, yes, of course. No, of course I did. And it's not a silly question at all. On the contrary, no, I would not even be able to define the oracle estimator. So I can't think of measuring some sort of distance between estimator and oracle. But I can tell you something. One would imagine that if we were to use the critical values computed with the true eta, so if I knew eta, the tail index, instead of having to estimate it, those critical values should reign supreme and should beat our methodology. We do a simulation exercise in the paper because we were asked by a referee. That's not the case. Even if you know the asymptotic critical values for the true eta, so in the simulations you play God and you say eta is equal to blah blah, and it is. Nevertheless, you don't do better than we do. That's not an optimality theory, but it's not a bad result either.
Yeah, but is that due to the Monte Carlo variance? No.
Who knows?
Thanks.
Very welcome.
Matteo, I have a question, if possible.
Yeah, go ahead, Luca.
Okay, I just was curious about your empirical application. You showed that the Johansen test basically does not pick out the right number of common stochastic trends in that example. I was wondering if you're also considering the, say, co-integration rank test under, say, heteroscedasticity or bootstrap controlling for heteroscedasticity if you have results in that case. And my second curiosity, just a curiosity, if you could manage to identify the stochastic trend driving the seven prices, if I understood correctly.
So Matteo probably knows this better than me, so. No, I'm not trying to pass the buck. I was just saying that you probably know it better than me. But
well, honestly, I didn't follow the question because I was trying to fix these problems with Zoom. So,
okay, no, don't worry.
Sorry about that.
No,
it does matter. We can discuss that in another moment.
But we have an estimator of the three. How many was that now? Of the four estimated common stochastic trends. So that might help, of course, up to some sort of linear transformation, but we do have an estimation of them. So.
Okay.
I think it's clear that the three oil prices have a common trend. That's expected, and that's absolutely clear. The other part is there might be one co-integration relation between the three. I think we did have the estimate of the loadings in one of the tables.
Okay.
Which could help.
Yeah. That is what I was thinking about.
Yes. Yeah, no, we have it from the factor model point of view. So we have an estimate of the loadings in another table, which I don't know if Lorenzo has at hand or not, but we do have that.
It is somewhere.
It is somewhere. Maybe you can
a second curiosity, then I stop promise. I was curious about the case where n goes to infinity. Okay. I was interacting with Matteo about, say, the technical issue. Probably I missed something, but I was, if I understand correctly, in that case you have something. You have the ratio between n to the power of something over t converges to 0 in order for your machinery to work. So I was wondering whether, imagine that I'm going to the data, whether which is the practical rule that you would give to a practitioner in order to select n in that case.
So in that case, you would need, at least in principle, to have an estimate of eta.
Okay.
An estimate of eta does not need, in that case, to be super precise, because then you will not use that estimate to choose the limiting law of anything, so you don't need it for critical values. So even if you don't want to estimate eta, you could do a test and check if eta, for example, is greater than 1. You could use a test for infinite first absolute moment and so on. And if you find out that eta is greater than 1, then n to the power of 2 over 1 minus 1, or whatever it is, over t going to 0 is your rule. So n should be such that n over t goes to 0 in that case. You could, so if n is much bigger than t, probably you need to take a portion of n. Which ones?
Okay.
I'm not, I would not know.
Thank you.
Okay, so I think
Matteo,
yes,
just one curiosity.
Yeah,
it seems that the crucial thing here is the tail index, but you have many different distributions with the same tail index. You can take, for example, like n independent student t with half degrees of freedom, or a joint student t, which is with half degrees of freedom, which they both have the same index, but the same tail index, but in one case the epsilon are independent, in the other they're not. They are dependent, actually. They have tail dependence on well, you also have other distributions with the same tail index, and I guess asymptotically nothing changed, but I mean, for example, what do you use in your simulation? Which
All the coordinates of all the vectors are independent of each other, and we use a power law, something that looks like a Pareto. The fact that the coordinates are independent of each other, yes, one could do it a bit more complicated.
Just a joint student T with eta degrees of freedom would do it, no?
Yeah, I mean, in terms of it's not what we do in the simulations, but we could. That would be a very, very nice idea.
Or well, it's not nice, but just
we don't need symmetry, so skewness could be.
Yeah, SQT also.
Asymmetry could be a possibility.
Bene, grazie. That's all I need.
Okay, I think we can probably officially stop the webinar here. If you want to stay, you are happy to see. I'm happy for you to stay in this room. There is no problem. I have to leave, Lorenzo. Sorry about that, but we'll catch up later as agreed.
Can I say something bad about Juventus now, or?
For me, you are everything.
For me, yes, you can say whatever
everything
you like.
say. For me,
no, Lorenzo, yes, so you cannot.
Ciao Camilla.
Ciao.
Non cominciamo. Una cosa, la call per Cagliari, quando parte?
Non lo so, però abbiamo tutto up and running, abbiamo le date e abbiamo i due, come si dice, abbiamo i due invited speakers.
Invited, sì.
Al coso lì che fate il 10 di giugno allo steering committee, io credo che Monica, Emanuela non credo che potrà venire, ma Monica vi dirà tutto, ecco. Secondo me la facciamo ASAP, nel senso che abbiamo tutto pronto.
Ok, perfetto. Bene, ci vedremo a Bertinoro.
Ci vediamo tra una settimana, no, un po' di più, tra 9 giorni. Con piacere, se non mi cancellano il volo, perché avete letto del casino di EasyJet, no?
No, che è successo?
EasyJet, in particular from Gatwick, sta cancellando 1 miliardo di voli per motivi che probabilmente sono anche scritti sugli articoli di
Io devo
giornale.
andare, Lorenzo, ci sentiamo dopo.
Ciao caro, ciao.
Vi lascio la stanza aperta, perché è mia. Se chiudo io vi butto tutti fuori, quindi vi lascio. Ciao.
Stop recording, Matteo, questo.
Infatti sta ancora facendo i recording.